Alright, hello everyone. It's the Diabolic tutor. And today we're just going to be continuing the fractions, not fractions, the exponents from the other day. So let's get started. Alright. So last time we covered the exponential rules, and that one's covered in the previous video. Today we're going to be expanding on that by working with fractional exponents. So basically the radical series for exponents. So when we're talking about the fractional exponents, we mean exactly that. So if you have a to the power of 3/2, then that would be the fractional exponent. This is to contrast with last time, which was just whole numbers. So we had a to the power of 2 type problems involving whole numbers like a to the power of 2, b to the power of 3, c to the power of -2 with integers as well. But this will be the focus of today. And thankfully, many of the rules that we covered for these ones will carry on to those ones. So rules 1, 2, 3, 4, 5, and 6. Again, those numbers are just arbitrary, not of particular importance. So the first thing we need to cover would be the notation of the situation. Actually, let me move a few things. Where is the chat? Not that there's anyone in chat, but well, let me move things over. Okay. Good to go, good to go. Alright, so again, with the thing of notation, typically most people's experience with fractional exponents is actually with the square root. So when you have rad a, for example, so we have the funky symbol right here. It's the radical symbol, which represents taking the square root of whatever value is inside. So in that situation, it would be taking the square root of a. So when you're evaluating these types of symbolic notation, if you had the square root of 4, for example, that's just going to be equal to 2. And then, just to review, why is the square root of 4 2? Because 2 times 2 gives us the 4 back. So if we consider this to be forwards, how to generate your number, you generate the number by taking the base number in question, and then you raise it to the second power, which means multiply by itself twice, and then that's going to yield a 4 value. So if we consider that going forwards, then taking the square root of that number will be considered going backwards, or it's called the inverse of the function. So again, going forwards versus going backwards, inverses will be become a lot more important when you're dealing with like stuff in pre-calculus, probably even algebra 2 by most standards. So the idea of going forwards versus going backwards is going to be more and more important, but not the emphasis of the day. All right, so again, continue on. Again, the radical notation, the square root is typically the first fractional exponent that most people deal with, but it's not taught as a fractional exponent in the beginning. So let's talk about that real quick. When you see the radical sign, there are actually kind of invisible numbers, as mentioned before. So quick review, if you have a particular term, x for example, and you don't see any other numbers, there are actually other numbers. There's the coefficient in the front, the invisible 1, and then there is the invisible superscript 1 for the exponent, and there isn't any subscript, thankfully. Subscripts are just for naming purposes, but you won't have to worry about invisible numbers for the subscripts. So just those two numbers for now. We have the invisible 1 and then the invisible 1. And we also talked about how you could just put anything over a fraction bar. There's also an invisible 1 right there. But there are even more invisible numbers. You will see when you get to Logarithms, they're also invisible numbers for that one and for this one, which is kind of annoying. But what is the invisible number for the square root notation? It's actually a 2 out in front. So technically you could put a 2 in your mind's eye. Don't ever write it, but there is an invisible 2 right there. And personally, I don't really like the radical notation. I believe it's for visual clarity. It's to look nice. But you can translate the radical symbol into a fractional notation. So this thing right here, let me color it something else real quick. So this one, you can translate it to a 1/2 exponent. So I guess there's no real reason why. It's just simply notation. But let's dissect that again real quick. So on the outside, I said that there was an invisible. If you don't see a number on this little radical symbol, that means that there's an invisible 2. If you don't see a number in the exponent, there is an invisible 1. So we have 2 numbers. And if you are aware of this translation, you can translate it into, again, fractional notation. This one goes up above, and then this one goes down below, right there. So how do you know that? Well, experience, I guess. If you've done enough problems, it kind of becomes internalized. But for now, we can revisit one of the old rules for division. So when you're doing division, there are some teachers who teach it like this. You have a fraction, and on top of the fraction is the quote-unquote the rider, and then below the fraction there is like the horse, the thing that is giving a ride to the rider. So person is like on the horse, and then the horse is right there. So the story goes like this. There is basically a house, and who goes into the house? Well, we hope that the person goes in the house. So the person goes in the house, and the poor horse, unfortunately, is outside. So, we're talking about no sheds for this poor animal. So basically, we have the 3 on the outside, and then the 2 on the inside. So, again, that's the way the story goes. The rider goes into the house, and then the horse goes outside of the house. The people house. Hopefully the shed, right? So I'm mentioning this story because you could actually adapt this story for the purposes of exponents. So again, there is the outside of the house, which is the 2. And then there's the inside of the house, which is presumably the person. So when you do this goofy story, you can say that the rider, 1, goes over, and then the horse is the ridden one. So it's going to be 2 on the bottom. So that's how you can translate from radical notation into fractional notation. There we go. So let's just practice a few of those. Again, you begin to internalize this when you actually do problems. It's kind of artificial to just sit there and memorize it, but hopefully the story is somewhat useful. But it depends on your brain. Alright, so if we have, for example, 3 rad, that's not how you say it though, but let's say it's like this. This is technically cubic root, so cubic root of c to the power of 2 inside the fraction. I mean, within the radical. So again, translating this, what's outside of the quote-unquote radical house, it's the 3. And then what's inside the radical house, it's the 2. So the rider goes on top, and then the ridden goes on the bottom. So c to the power of 2/3. Yeah, this is just notation. If you have b inside the 4th root, and then b is raised to the 3rd power, again, just translate it. I'm going to stop mentioning the story because it's kind of goofy. So 3 goes on top, and then the 4 goes on the bottom. One more for the road. So if you have the 7th root of d to the power of 10, you can translate this directly into fractional notation. So we have d to the power of 10 over 7. So notation has been covered. And now we're going to just basically perform some operations like we learned before. So if you recall, if you have same base with an exponent times same base with also an exponent, all you need to do is you need to summate the bases. So I'm sorry, not the bases. Summate the exponents. You have 3a's multiplied here, and then you have 2a's multiplied there, so altogether you have 5a's. So summation. And then if you have a to the power of 3 in parentheticals to the power of 4, for example, this one is distributive property of exponents, so 4 times 3 is 12. Easy. And if you have a to the power of 10, and then this is over a to the power of 3, for example, then all you need to do is subtract it. So you have a to the power of 7. We covered this in depth last time, so we're going to just rush these. And then lastly, if you have a to the power of 0, for example, then it's just going to be equal to 1. Most people would say that 0 to the power of 0 is 1. I just tend to avoid it altogether because I don't like this idea. Alright. But now let's apply it to the fractional situations. So if you have a to the power of 2/3, and then you're multiplying that to a to the power of 1/3, you're going to do the exact same thing. Same base here, multiplication. All you need to do is mechanically add the exponents. So thereby getting, this is old school pre-algebra coming back, so 2/3 plus 1/3, they're the same type of fractions, third type fractions, so therefore if you have 2 of the thirds and then you have 1 of the thirds, altogether you have 3 of the thirds. So simplify that, please, and then you get a to the power of 1, and we're good to go. But don't write the 1, because it's supposed to be an invisible number, so therefore, just a. So seems simple enough. And of course, the annoyances come when you have mismatched denominators. So you have b to the power of 2/7, and then you're multiplying that to b to the power of 1/3. And this is kind of annoying. So same base, multiplication between. So all you need to do is follow the algorithm to add those exponents. And again, they are mismatched. Simple rule is to simply just do cross multiplication, but make sure you check common denominators first. 7 is a prime number, and then 3 is a prime number, so you don't need to worry about LCDs. So these ones cross multiply. All right? So we have 2 times 3 is 6, and then the 7 times the 1 is 7. So that's simple enough. So let me show the work. So again, we wish to change this one to match the denominator of this one. So top and bottom times 3. So 6 over 21. And as for this one, it becomes top and bottom times 7. So 7 over 21. And as I said before, you could just simply do the cross multiplication since there are no common factors on the bottom, so that would get you the 6 plus the 7, which is a shortcut right there. So summating those ones, we have 7 plus 6, which is 13. And then we're good to go. So not too bad. Not too bad. Again, the exact same rules, you just have to deal with annoying stuff like fractions. So now we have c to the power of, what's 1/3, and then we're multiplying by c to the power of something like 5/6, let's say. So when you're doing a thing like this, again, cross multiplication is not always the most efficient strategy, because 3, you can easily bring it up to 6 by multiplying top and bottom by 2 over 2. So we have 2 on the top and 6 on the bottom. And then in that way, you could just summate the top portions, and then you're good to go. So 7 over 6. Alternatively, if you had if you had done cross multiplication, then you have a little bit more work to do. So again, if you did 6 times 1, 6, and then 3 times 5, which is 15, you're going to get that over 6 times 3, which is 18. So unfortunately, you're going to get c to the power of 21 over 18. And if you can recognize it, it's simplifiable. So you would simplify it by dividing top and bottom by 3. So 7 over 6, which is consistent with the first answer. It's just slightly less efficient. Okay. And of course, if you may have noticed, this is actually an improper fraction. Then this is a quote-unquote proper fraction, and this is proper. So should we do anything to this one? And yes, we should, because unfortunately, even though this is technically a correct answer, it doesn't look beautiful, which is a recurring theme in mathematics, right? So if you recall from your pre-algebra, algebra 1 days, if you have fractions and you have improper fractions, you're supposed to change them into proper fractions. So if you have 7 over 6, you're supposed to change it. How many 6's fit into 7? 1 6 fits into 7. But then you have a leftover of 1. So 1 and 1/6 is what you're supposed to change things. It's change this improper fraction into this one. Again, why is it not proper? I don't know. Someone didn't like it. So let's change it. So changing this one, we have c to the power of 1 and 1/6. All right. So unfortunately, this is also not the final answer that you should report because it looks really messy. There's a coefficient, not coefficient. There's a whole number 1, and then there's a fractional 1/6, so you're supposed to separate those as well. But luckily, we can call upon the exponential rule number 1 from last time, right? If you think about this, this is simply 1 and 1/6, which and is just simply summation, so it's technically 1 plus 1/6. So you can think about it in your mind's eye. You don't need to write this down, but it'll be 1 plus 1 and 1/6. And if you recall, if you have same bases, all you need to do is add the exponents to get to there. Well, now we're going backwards. We're starting from the exponent, and then we're splitting it apart. So this one is going to transform into c to the power of 1 times c to the power of 1/6. So again, this is just the inverse of our first rule. So the first rule is to add the exponents, but now we are separating the exponents, changing it to multiplication, same base, same base. Term number 1, term number 2. And finally, we can clean this up as c times c to the power of 1/6. You can't even see that. You see, we got the c, but you cannot see. All right, here we go. There it is. So, and you would think this is the final answer, right? Unfortunately, it is not the final answer because this is quote-unquote not beautiful. We're supposed to change it back to radical notation. So you copy the c in the front because that's a whole number exponent, so that's okay. But this one, remember, the rider goes into the house and then the horse goes outside the radical house. So we're going to put radical sign. What type of radical? It's the 6th root. So the 6 goes right there. If you're not comfortable writing it, maybe some people, you'll see in some books or some handwritten stuff, they're trying to make it really obvious that the 6 is the radicand. But I'm going to leave it like this. And when it goes in the house, it's the rider, the 1, and it's c to the power of 1, but you don't write the 1 because it's going to be invisible. So therefore, there it is. Now is that the final answer? Yes, we've finally arrived at the final answer. So this, you're good to go. So how much of this was tedious work? Well, this one's kind of tedious, but again, as you get the hang of things, gradually As the synapses are strengthened, the electrical signals in your brain are strengthened, you won't need to go through these entire motions. So this one will become second nature. Summoning those ones, you probably don't need to explicitly write these steps. This one right here, well, you could technically skip from here to here, right? If you're comfortable. But go through the motions first so you can internalize the rules, and then once you internalize the rules, then you can start skipping steps, as most people would suggest. Right, so continue on. And now let's start to incorporate the radical notation, because that's how you will see things written. And the irony is that a lot of typing programs, at least back in the days, it's very difficult to type in the Radican symbols. It's very difficult. You don't have programs that could easily do this. I remember making worksheets back in the days where they give you the radicals. All they give you is this, and then you have to go find your symbol, and then you need to put the super score, and then super score, and then super score, and it looks really disgusting. I hope they fixed it in Word documents now. I'm not sure. But regardless, this is handwritten, so we can avoid that altogether. Alright, so we're going to do fourth root of d, and then it's going to be to the power of 3, and then we shall multiply that to, what is it? Let's do fifth root. No, let's do basic square root. So we'll do the typical problems first. So we have something like this. Again, it looks very beautiful. Well, maybe that's arguable, but it looks nicer than fractionals. But in my opinion, it's best to change it into fractional notation. So this one right here, changing it to fractional notation, this one goes on the bottom, and then the 3 goes on the top. So d to the power of 3/4. And again, this one, there are invisible numbers. If you don't see a number in the Radican, that's called the Radican, there's going to be a 2 here, and then there's no exponent, but there is an exponent. It's the invisible 1 times d to the power of, on the top, denominator is outside. There we are. So unfortunately, they are mismatched exponents. So the easiest thing to do is to get the 2 to match the 4. So top and bottom times 2 for that. So we're going to get d to the power of 3/4 times d to the power of 2/4. So I'm just showing my full steps when you're doing this for scratch work or whatever, and you're not really concerned if anyone's going to see your work and criticize you. What you can do is you could just write it directly on the original problem not original problem, the one you copied down. So you would write 2/4 there, and then you just summate to get 5/4. So you don't need to keep writing everything over and over like what I'm doing right here. So this is just for the sake of visual clarity, and if you wish to trace the work. Alright, so we get the d to the power of 5/4, and again, unfortunately, this is not the most beautiful looking answer. We can separate it into d times 4th root of d. So if you're comfortable, you could skip straight to the answer like so, but I'm going to show the full work again. This one, improper fraction, so you're going to split that into 1 and 1/4. Again, that's technically 1 plus 1/4, so using reverse exponential rules is going to be d to the power of 1 times d to the power of 1/4. This one, you have to back translate it into fractional notation. So we're going to make the 1 invisible again, and it's times 4th root of d, and then you're good to go. Final answer. The most beautiful you can get the answer to become. So far, so good. Not too bad. But let's talk a little bit more about the radical mechanics. Actually, let's go back to this one. You can actually avoid changing it into fractional notation if you wish. So this one right here, if you understand that this is a fraction, you don't have to visually transform it into this form. So you can see that the outer number is 4, and then the outer number, which is technically invisible, but it's actually 2. We can actually leave it in radical notation, again, if you're comfortable with the idea of it. So it's going to be 3/4 as an exponent, and this one, you could actually just multiply those exponents by 2. So 2 there, and then 2 there. Now that these exponents are matched up, you could actually just summate the, I think these are called radicands? Wait, what are they called? I think these are called radicands. I don't remember anymore. Terminology is not super important unless you're talking with your colleagues. So let's avoid the jargon, right? So we keep the same fraction. It's the same fraction type. It's 4th radicand type. And then this is d to the power of 3, and then this is d to the power of 2. This becomes d to the power of 5, which should feel very familiar, because if you think about it, this thing right here, you can technically factor out the 4th root. So it's going to look weird, but just trust me on this. Let me show you. So this one is d to the power of 3 to the power of 1/4. Now this one is technically, you have to be very careful, because d could be a negative value. So most problems avoid the situation by telling you that d is a positive number. And you will see that in textbooks because it will avoid a lot of headaches. But in this case, d cannot be a negative value, because that would, you can't take the 4th root of a negative value. Just like you can't take the square root of a negative value, because you're drifting into imaginary numbers territory. But more on that maybe later. So this one, again, you can translate it into this form, assuming that d is a positive number. Otherwise, things get kind of screwy. And then times, same thing here, d to the power of 2, and then on the outside, you can put it as 1/4. So does this look familiar? So if you have, for example, a to the power of 1/4 times a to the power of 1/4, you can just simply factor out the 1/4. So what I'm saying is we can bring this 1/4 outside of the parentheticals that we can just slap on, the brackets that we can just slap on. So it's going to factorize into d to the power d cubed times d squared, and then outside the brackets is 1/4. Just apply exponential rule number 1. So d to the power of, we have 3 here, and then we have 2 there, so 5 d's multiplied together, all in total, to the power of 1/4, and then you change this back into radical notation. Horse goes on the outside, rider's on the inside. Well, technically this is the rider, right? But it's 5 times 1, but we don't put times 1. So there it is, same thing as before. So this is just showing the mechanics about why we can do this part right here. You don't always have to do this because it's a lot of work. It's a lot of work to show. So if the radicands match out there, you could just simply multiply the innards of the radicals. So I guess showing a little bit more work. If you're uncomfortable not showing enough work, here, we'll do it like this. So same radical here, same type of radical. This is 4th root times 4th root. So you can multiply that directly into the house, so to speak. So it'll be d to the power of 3 times d to the power of 2. That's why we can do it. Again, the reason why we can do this is shown there. And then just clean up step. So it becomes 4/4 root of d to the power of 5. This is technically not the answer you're supposed to report in the end. It's technically correct though, but it is an improper fraction if you translate it. So you have to simplify this. And the way you simplify this, you can do it in this particular fashion if you translate it into fractional exponents, or you could just think about it in terms of how many numbers fit into how many numbers. If you recall, this thing right here translates directly into here. So if you need the mental bridge, you can change it into fractional notation, which is what I recommend in the beginning. But how many 4s fit into that 5. 1 4 fits into the 5. So that's how you quote unquote bring out D. But fitting 1 4 into 5, you still have a leftover. So 5 minus 4 is 1. So there's 1 D left over. Left over in what? In the 4th root. So this is where, again, the notation, depending on how you write things, might become illegible or it might be confusing. I'm going to put a dot here just to be absolutely, just to convey my thoughts exactly, because if you don't put this dot, people may misinterpret this as D to the power 4. So they might go, oh, do you mean this? And that's not what you meant at all. So other people, they like to put this hook part right here really exaggerated, so they put something like this, which again looks really awkward to me. I really don't like this. This is not my preference. So multiplication and then 4th root, we'll do it like this. And that's your final answer. There it is. And of course you have to say, because in order to quote unquote yank that out, you have to report that D is not a negative value. Well, make sure you double check the beginning problem. So if you put a negative value into there, you can't take the 4th root of it, because if you cube it, it's still negative, and you can't take 4th root. Even roots, you cannot take even roots of negative numbers, because imaginary territory. Again, more on that maybe another time, maybe not today. But it pays to double check, because trickier problems will exploit the fact that most people don't really cover this, or most people ignore it because most problems don't really cover it that much. Okay, so again, speed just comes from doing more problems, but key is to understand what you're doing. So now we're moving on to letter E. So if we have e to the power of 3 within the 4th root, for example, and then we have multiply times, this is going to be cubic root of e to the power of 2. So again, common mistake of some sorts is people just go straight to multiplying those two. So they're like, oh, okay, I'm going to multiply e cubed times e squared, and that's going to give us e5 if they follow it correctly. If they follow the wrong rule, it's even doubly wrong, so they'll get like e to the power of 6. Remember, when you're multiplying same bases, you add the exponents. So don't conflate the rules. So 3 plus 2 gives us 5. And then, of course, this part is the one where things get kind of dicey. So they might do 4 times 3 to get 12, which is wrong. Or they might do 4 plus 3, which is 7, which is also wrong. So please don't do this. So what's happening? What's the underlying mechanism for this one? Well, first we'll change it to fractional notation. So you'll see why you can't do that. So this one translates into e to the power of 3/4. And this one translates directly into e to the power of 2/3. So back in the days, you'll learn that adding those ones is wrong. You cannot do it like that. That is the wrong way to do this. That kind of stems from one of those philosophies of maths. You can only add, okay, this is going to be a tangent. It might be a long tangent, so if you're watching this on the VOD or whatever, you could just simply ignore this. You could skip to the part where I'm going to delete this off of the face. So again, touching a little bit on the philosophy of math. Yes, there is a philosophy in mathematics. It's not as absolute as we would like to think. I guess that's some school of thoughts in mathematics, right? Do you believe that math is inherent in the universe, or do you believe that our math is just simply the rules we came up with ourselves and technically isn't part of the real world? I'm actually in the camp of the former. Math is all fake. So here's tangent. Here's the tangent we're talking about, not tangent lines. So if you have or if you have x, for example, 2x, and then you're adding that to 3x, we can summate these two because philosophically x here is exactly the same thing as the x there. So all we're doing is we're collecting the same types of stuff. So we have a type of thing, x type here. How many of those do we have? We have 2 of those x types. So there are 2 x's right here, and then we're adding that to the same type of thing so we can collect them together. How many of those? We have 3 x's right here. So 2 x's here. We can consolidate it with 3 x's there. So in total, we're supposed to have, in the perfect world, 5 x's. All right. And why am I mentioning this? Oh, the reason why you can't add 2 fractions together. So if you're trying to add, for example, 2/3 plus 1/3, there's not much you don't need to manipulate much. You could just simply add those two up. And the question is, why is that? Well, you have 2 of something. You have 2 of, remember the mathematical English translation, of is primarily multiplication. So you have 2 of these thirds, and then you're adding it to technically 1 of those thirds. So if you have 2 of those third types, and then you're adding it to 1 of those third types, you could just simply consolidate those. How many third types do you have? You have 2 plus 1. So you have 3 of those third types. But you could simplify this. Final answer. So if you have 3 third types, you could just simply combine them and call it a whole. So how is it related to what we're talking about? If you have, for example, 3/4 plus 2/3, these are technically different types of stuff. You have 3 of these fourth types, and then you're trying to add them up to 2 of those third types. Unfortunately, these types are not the same, so you can't philosophically add those two together. If you have 3 oranges and then you have 2 apples, you can't say you have 5 apples. You can't say you have 5 oranges, nor can you say that you have 5 apple oranges. That makes no sense. You can, however, you can rename those into the same types. So rather than calling an apple and an orange, you could just call them, in the colloquial sense, you could just call them fruits, right? I think in botany there might be some weird nuances because human definitions, right? But you have to change them to the same types of names. So again, these ones are different types, so you cannot simply just say, oh, we have 2 here and 3 here, so we have 5 of them. 5 of what? Is it 5/4? No. Because you have 3 of those fourths there, but these are not fourths. And nor can you call these ones 5/3, because you have 2/3, but you don't have 3/3. So neither of that makes any sense. So some people might default to saying, well, you know what, maybe we have 2 of those 7ths, and that one also doesn't make any sense because 7 types is distinct from fourth types. It's numerically unequivalent because the mechanism to get from here to here requires equivalent fractions, which involves multiplying by 1. So you can't just make it up. So all of this is just to simply say we cannot add 3 plus 2 gives us 5, and then 4 plus 3 gives us 7. So this one is not a valid answer because that's not the algorithm you need to learn, because philosophically you're adding different types of stuff. So what do we got to do? We got to get them to become the same names. So if you have 3/4 plus 2/3, again, philosophically you cannot add those up. You have to change them to become the same type of thing that you're adding. So top and bottom will be times 3, and then top and bottom times 4, following best practices for lowest common multiple, or lowest common denominator. So now we could summate. So 9 plus 8 is 17. And then 12, 17 of what? 17 12th types. So 17 over 12. And that is the valid thing that you can do. And that's the end of the tangent. So if you didn't care for that, that's okay. Nobody's watching it right now anyway. You could always skip on the VOD. So here we are again. We're philosophically we're saying that we cannot summate those to get 5 over 7, which is what I'm trying to, which is the explanation for why you can't just simply get e to the power of 5 inside here, and then 4 times 3 exponent gives us 7 if you summate. So this is the wrong answer. All right, so mechanistically, what do we need to do? I'm going to stop trying to put so much work. So this one, again, these are mismatched, so all you need to do is just do the old cross multiplication. So 3 times 3 is 9. 4 times 2 is 8. So summate those two. 9 plus 8 is 17. Common denominator is 12. All right. So again, you could always show full work. If you ever get the summating or multiplication mixed up, you should always do the full work until you internalize it. So we have time. I'm going to show work then. Again, if you happen to stumble upon this video, feel free to skip. So there we go. Such is the advantage of technology, archived technology. So there we go, and then we have e to the power of 9/12, and then times e to the power of 8/12. They are the same. This is the same base, so we could just simply add up the exponents following the algorithm. But this requires its own algorithm, adding exponents. You have same denominator, so you keep the same denominator. And then 9 plus 8 is 17. There you go. Again, this is not the final answer to report because you have an improper fraction. So if we skip the work, if you're comfortable with it, how many 12s fit into 17? Only one of them. How many remain? Subtracting 12 from the 17? 5. What type of radical is this? This is 12th type radicals. So 12th root of e to the power of 5 times e to the power of 1. Don't write the 1. And now you've won. Well, I guess it looks kind of ugly, right? Let us strive for legibility. Alright, that's the best I can do. I don't exactly pride myself on my penmanship, but good to go. So this is from the fractional viewpoint. If you wish to translate it from radical notation into fractional notation, or you could use the more risky maneuver. You can see there's a 4 out here, and then there's a 3 out here. You can convert those each into 12. So you can change it from 4th root to 12th root, but to do that, again, this is technically a fraction, so top and bottom times 3. So this one times 3 gets you here, and then this one times 3 gets you there. Again, this is technically a risky maneuver because you might have negative arguments, or I'm sorry, negative bases, but we're assuming e is a positive number, then it's safe to do. If it's not, you always have to back plug in your answers into the original just to make sure there aren't any weird domain issues. Okay, so we get here. This one we're trying to match it up to the 12th, so times 4. So it becomes, I'm sorry, not 4, 12th root. So this one times 4 gets you here, and then this one times 4 gets you there. Equivalent fractions again. So 8. As you see, it's analogous. This is analogous to that step, and then this one is analogous to that one. But again, we're trying to avoid excessive amount of work. So if we're starting from here, we can get to this work. And once you get to this work, they are now the same radical type. So you can simply multiply this one times this one. But to show a bit of work, extend the old house. So it's e to the power of 9 inside the radical times e to the power of 8. At which point you can consolidate. Some people allow you to skip this step. So we have 12th root, sum those up. There we are. Unfortunately, this 17 is greater than this 12, so we can yank out some e's. So how many 12s fit into 17? Exactly 1. So e to the power of 1. And then how many leftovers will remain? Well, 17 minus the 12 that we took out is 5, but they're still inside the rad 12. So there it is, e to the power of 5 left over. And that's it. Is it consistent? Yes. So this answer is consistent with that answer. As you can see, this one is a bunch of work. This one is slightly less work if you wish to avoid translation. This is like the bilingual situation, right? So if you know Spanish, for example, and then you know English, then sometimes you can translate to Spanish first, and then you translate it back to English. But why bother if you could just go directly with the language? And it's slightly faster. Not tremendously faster. But like I said, I think it's nice to know fractional exponents because they make a lot more sense, because this one feels a little bit more foreign in terms of language. Alright. So good so far? Yeah. So let's do some fancier problems, of course. Now you're going to start dealing with fractions within your fractional exponent problems. So here we go. Let's say we have the 7th root of a fraction. We're going to have a to the power of 3. And then, oh, you know what? Let's do only one letter first. Let's do 2 here. And we're going to do b to the power of 3 down here. So this is obviously kind of a mess. But let's dissect this real quick. To do the problem, you don't need to do this, but I'm going to illustrate just what are the components of this thing right here. So technically, you can split the radical into the top radical. So you can split it into 7th root of 2 up on top, and then you can split it into 7th root of b cubed on the bottom. Again, this is not necessary to do your problem, but just to show you the mechanics of it. A dissective approach to show you the components, just to illustrate that this one is its own problem, and then this one you could treat it separately as its own problem. So in this case, if you try to take the 7th root of 2, you don't need to do anything, because this is 2 to the power of 1. So mechanistically, no whole 7s can fit into 1, so you leave it alone. And then mechanistically, no 7s can fit into a 3, because remember, it's a fraction. This is 2 to the power of 1/7. And then that is b to the power of 3/7. So no improper fractions to speak of, and you may be tempted to report this as your final answer. In most cases, you'd be deducted points, unfortunately, because beautification. So this one is called a fractional exponent in your denominator. So what you're supposed to do is, for your final answers, you're always supposed to have whole numbers for your exponents in the denominator. And why is this? It's probably because teachers want to have an easier time checking students' homeworks. So if they're checking 30 students per class and they have like 3 math classes, an example, that's going to be 90 problems to check, if they do check at all. So 90 problems. They want all the answers to look the same. So if all the answers look the same, you just need to check the answers at a glance. So that's probably why. There's no real reason why you have to do this. At least, I don't think so. Because this is translations. So this one. So the question is, what are we supposed to do for this problem? Unfortunately, we're going to have to go back in history, your mathematical career, just a little bit. So when you have something like 2 over square root of 2, you may have learned the algorithm to just multiply the bottom by the same thing. So you multiply top and to rationalize the denominator is what this is called, because this is an irrational number. So you're supposed to follow convention. You're not supposed to have radicals on the bottom as an extension. This is just an extension of this beautification process. You're not supposed to have fractional exponents on the bottom for the same reason why this one, because this is technically fractional exponent, right? Okay, so the algorithm that most people learn and kind of internalize is to just copy paste this thing, multiply by root 2 and then root 2, and this serves them very well, but unfortunately it fails when you're doing these type of problems, and I'll show you why after executing this one. So this one is root 2 times root 2. So anytime you have the same roots, you can negate them and therefore get 2. And then this one is nothing to be done. But cancel the 2, and then final answer is just root 2. But again, mechanistically, what is happening in this situation? It's not clear in the radical notation, which is why I recommend thinking about it in fractionals first. So we have 2 over 2 to the 1/2 power. Because remember, invisible 2, invisible 1. Fractional exponent. So what are you doing when you're choosing to do this algorithm? When you're following this algorithm, you're technically multiplying again. Invisible 2, invisible 1. So 1/2 here, and then 1/2 on the bottom right there. So when you execute the algorithm, when you evaluate this mess, you're going to get 2 times 2 to the power of 1/2, and then the bottom portion. This is where the magic happens. And then you see 2, same base, same base. All you need to do is add the exponents. So it becomes 2 halves, which is simplifiable. So on the simplification, this one is 2 to the power of 1, but don't write the 1. Cancel, cancel. Change this back, translate that back into radical notation. Don't put the 2 because it's invisible. Don't put the 1. Final answer. So mechanistically, you can see why this strategy works, why this algorithm works. Why do you choose to multiply this one to this one? It's because you want to complete the whole, because 1/2 plus 1/2 gives you 1 whole, right? That's in essence why you're using that algorithm, and this is why some people fall into this particular pitfall. So when they see something like 1 over, let's say, cubic root of b, and then they choose to follow the algorithm, unfortunately the algorithm fails. They're going to multiply top and bottom by cubic root of b, and then cubic root of b. So thinking that it's going to solve the problem, thinking that this one becomes just solid b. But unfortunately, the mechanism doesn't work out. Because why not? Well, I think it becomes clear if you check it from a fractional viewpoint. So this one again translates into b to the power of 1/3. Those ones are all technically 1/3. You can see same base, same base. If you summate the exponents, you're going to get 2/3, which is still a fractional exponent that you cannot simplify. So that's why this one fails to rationalize. So what are you supposed to do then? Well, you want to generate a whole number. So all you need to do is ask yourself, if this is 1/3, how much more do I need to reach a whole number? Well, 3 minus 2 is 1. I'm sorry, 3 minus 1, I already said the answer, is 2. So there it is. So top and bottom. But make sure this has to be 1 equivalence. So the top one also needs to be 2/3. So now, when you multiply the base, the exponents complete to make 3 out of 3, which is 1 whole. And let me keep the work. This is simple operation. Final answer again, we gotta beautify this. So cubic root of b squared. So this will be the final answer to report. Now, is that kind of a pain? Yes. Again, if you wish to translate it into fractional exponents, you can get here. But if you're comfortable with the radical language, all you need to do is consider at this stage, let's delete it first. So what do we choose to multiply to top and bottom? Again, don't mindlessly follow the square root algorithm, because that one works only for square roots. This one is 3 and technically invisible 1. So what do you need to multiply to beautify the situation? Well, how do you make a 3? If you have just 1, you need to add 2 more, so b to the power of 2. What type of radical is this? We need to keep the same type. Cubic root. So top and bottom must be the same, 1 equivalence. Otherwise you're changing the problem. So now it makes a lot more sense. Since this is the same radicand, you could simply multiply. So cubic root of this one times this one. Identity. You could probably skip this step. If you see 1 plus 2, you could skip it to right here. All under this one. Copy paste. How many 3's fit into 3? Just 1, which is our whole intention. So B, and then the top one, nothing to do. Why not? Because no whole 3's fit into 2. So this is the final answer to report. Again, you could probably skip this part if you understand that you need to match this 2. You need to add this 2 to this current number in order to get a whole number. 3 divided by 3 gives us 1. This is now no more fractional exponent, so we have successfully beautified the bottom, which is called rationalizing the denominator. Again, there's no real reason. There's no real rationale for rationalizing, in my opinion. Alright, so let's, again, well, technically I didn't do this problem right here, did I? Didn't, but that's okay. There's not much to do. Besides rationalizing, because what we did here is essentially what we need to do for this one. You know what? Now that we're here, why not? So let's clean that up. It's kind of a mess. You know what? We don't need this part. Let's start all over. Alright, so when you're presented with this type of situation and then you're asked to evaluate this one, let's make a few notes. Number 1, this is exponent 1. How many 7's fit into 1? None, so we leave this 2 to the power of 1 alone. How many 7's fit into this 3? None, so not much to do, right? But let me split this radical just to illustrate a few things. So you could split into the top, and then you could split it into the bottom. This is simply one of your exponential rules. Exponential rule number 3, was it? I don't remember. It's not important. Who cares about names? Unless you're trying to communicate your ideas. Okay. So the reason why that rule works is because this one, again, translates into 2b cubed parenthetical to the power of this thing, which again, 1/7. And then following distributive property of exponents, you can distribute this to here, and then you can distribute this to there, thereby getting this to here. And this one translates back into that one. So that's why you could split the radical. But You don't always have to justify your steps once you've justified it once. Maybe. Alright, anyway. This one, again, we saw that no whole 7s fit in there, and then no whole 7s fit into there, so this one is not much to do. However, the bottom portion is fractional, and you need to beautify your answer, so hence you need to rationalize your denominator. So can't leave it as such. So how do we do this? Again, the losing strat is to multiply by the exact same things, which may be a bad habit picked up by some people when they're doing early exponents with just square roots. So this is the wrong strat yet again. Okay, so don't copy paste the exact same thing, because 3 plus 3 does not give you a 7 whole. So rather than that, we need to bring this up to a 7. So mechanistically, this needs to be a 4. So keeping mathematical equivalence, the top one has to be times 7th root of b to the power 4 as well. So when you do this one, now all we need to do is summate the exponents following exponential rule number 1. Keep the same radicand. So 3 plus 4 is 7. And then this part right here, that's going to be a goofy nonsense. Well, this one right here is 7th root. That one right there is 7th root. So you could simply multiply this innard to that innard. Again, that also comes from factoring exponents. So you have 2 to the power of root 7, and then b 4 to the power of 4 to the power of root 7. You could factor out the exponent to get this, which translates into this. But that's a lot of work. So if this one matches this one, you just multiply inside times inside. So again, root 7 matches root 7, which is what we chose. We deliberately made it that way. So it becomes the 7th root of inside times inside. Again, it stems from exponential rule. There it is. How many 7s fit into 7? 1. So that's how you, quote unquote, again, bring it outside of the radical. This part right here, nothing to do, because again, no 7s fit into 1. No whole 7s fit into 1. No whole 7s fit into 4. So the top one, you can leave it in radical form. And that's it. Final answer. Again, the assumption is that b is not equal to... Actually, no. In this case, it's okay. b can be a negative number because you're doing 7th root, which is an odd root. And this is odd, so no negative shenanigans to really worry about. However, b cannot be 0. Kind of pedantic. Most people just simply ignore this as they're doing the problems, but technically, as a person who tries to follow math rules reasonably well enough, you need to put this up here. b is not 0. Final answer. Alright. Moving on to other problems, of course. We have x. Let's do a more complicated problem. So we'll do 4th root of a to the power of negative 3 when we're incorporating negative exponents as well. Just to gradually step up the problem. You know what? Let's put normal numbers as well. Typical numbers. So we have 32 here. And then we are going to have a to the power of negative 3 and then b to the power of 2. And then all over c to the power... let's not do evens just yet. You know what? I made a mistake. The reason why I'm going to change this is because I want to avoid talking about positive, negative nonsense. So let's keep it as cubic. Cubic right there, which means I should uptick this one to 31. And then we'll have c to the power of 5 on the bottom. Alright, so there's a lot of stuff to do for this. But all you need to do is adopt a dissective approach. Just be like a doctor or whatever, right? Try to narrow in on different parts. So we are taking the cubic root of what? This whole thing? This is a whole Medusa of a problem, so just break it down. So we have a 32 here. We have a to the power of 30, negative 31 there. We have b to the power of 2, and then we have c to the power of 5. So multiple things to contend with. Assume a, b, and c are positive numbers to avoid dividing by 0. Disclaimer. So what can we do? Well, I would suggest changing this into a positive exponent and then start breaking down large numbers to see if you could divide stuff. Alright, so let's change it. We'll not change this to fractional exponents anymore because that's just conceptually to explain what you're doing. Or not conceptually, but to mechanically show what you're doing. Break it down. So 32 factorizes into 8 times 4, which is just 2 times 2 times 2 times 2 times 2. So 2 to the power of 5. Again, negative exponents, I would pass it to the bottom. So a to the power of 31, and then b is positive exponent, we'll leave it up above. C power 5 is positive, we'll leave it where it currently is. Take a step back. So at this point, you can see how many 3's fit into 5? 1. How many 3's fit into 2? None. No whole 3's at least. How many 3's fit into there? 10. But you'll have a remainder. How many 3's fit into 5? 1. So at this point, you may be tempted to start dragging things out like this. Again, how many 3's fit into 5? 1. How many 3's fit in there? None. How many 3's fit into here? 10. How many 3's fit in there? 1. Let's see the power of 1. And now you would deal with all the leftovers. You took out 3 from the 5, so you should have 2 remaining. Nothing to do with that squared, so we left that alone. How many 3's fit in there? 10, which is minus 30, right? Because 10 times 3 is 30. So we removed 30 10s, took the cubic root, which gives us 10. So we have a remainder of 1a. How many 3's fit into this 5? 1. So we have a remainder of 2 on the inside. So you may be tempted to do the work like this. And honestly, it's not a bad route to take. We can proceed from here. Don't forget to copy paste the cubic root. Alright, so at this point, this is technically a correct answer. It just looks ugly in a number of ways. Number 1, make those invisible. Number 2, technically fractional exponents on the bottom. So this one is looking good. We're just going to copy paste that. Not much to do with it. Just please make those invisible. So times what? So cubic root. This is where the mechanics can get kind of messy. This one, there's not much to do with that. I'm going to change it back to 4. Leave that alone. You don't need to rationalize the numerator, just the denominator. So here is the strategy. Yet again, we wish to change this into a number to make it fully divisible by 3. The easiest one to reach is to make this one into a 3. But you can't just willy-nilly write over the 1 and make it a 3, right? So mechanistically, we have to multiply top and bottom by a to the power of 2 inside the house. Now, does that feel safe? Well, yes, it is safe. So the long way to do it is to make sure that the radicand is the same thing. So you do a radicand a to the power of 2 and then a to the power of 2 times. So that way, since the they're both cubic roots, you can multiply this one times this one. So 2 plus 1 is going to get you the 3. That one you could take the cubic root, because 3 is divisible by 3. So yes, you could show your work like this one. But personally, I'm a little lazier when it comes to doing my own work. So I would just extend this little radical symbol just a little bit, and I'll choose to multiply by a power 2, a to the power of 2. That's safe because you're technically multiplying this inside number by 1 equivalence, and nothing is 0, so you're okay. So that's what we're doing mechanistically to complete the a, because again, a squared times a1 gives us a cubed, which is perfectly matched with the cubic root. Perfect. So you can kind of extrapolate what's going to happen with this one. This is already at 2. It's not quite divisible by 3. So you just need to bring this up to match the 3. So exponential rules, you need to add 1 by multiplying by c power 1. But you need equivalence, so times the top as well. Alright. So once you acknowledge that, we can proceed to clean up step. Again, this gives us a cubed, this gives us c cubed. And what do you know? Divisible and divisible, so we can bring that out and bring that out. So we have a to the power of 10 times c, and then again you have to multiply. Let me just show the full work. This one, 3 goes into 3 once, so a to the power of 1. 3 goes into 3 once, so c to the power of 1. Make sure you put it on the bottom since these ones are in the denominator. Stick them in the denominator. Don't magically shift them to the numerator, please. And then, of course, nothing happens right there besides this one. So it's times a to the power of 2, c to the power of 1. Almost forgot to add that. Alright, so cubic root, none of these should be divisible by 3 because of the mechanics. So b to the power of 2, a to the power of 2, and then lastly times c to the power of 1. Drag it all the way over. This is a mess. This one's not in alphabetical order, so there's a little bit more work to do. So final answer. 11. 1 plus 1 is 2. And then times cubic root. Yeah, I made this the ugly one, I'm sorry. 4. Let's put it in alphabetical order. So a squared, b squared, and then c. Drag it all the way over, and that is the final answer. You can also put this up on top with to accompany the 2. So I guess technically not the final answer. But you know, depends on what your teacher is willing to accept, or whomever cares, because I'm not grading you. So I think if you write your answer like this, there ain't nobody who can complain about this. I'll put a dot here just to be safe. So final answer. There we go. Alright. So again, the trick for rationalizing the denominator is to make sure you want to bring whatever exponents you have on the bottom, just need to multiply by the corresponding same bases, but make sure the exponents summate to become that exact value. Can you summate it to be greater than that value? Could we have, instead of picking 2, could we have instead chosen 5? 5 on the bottom here, and then 5 on the bottom there. You most certainly can, but that's just extra work, unfortunately. So 5 times 1 will get you the desired 6, which is divisible by 3, and then you'll drag out the a squared. But unfortunately, this one introduces a 5, which is divisible by 3. So you're gonna have to yank that out, and then this one will cancel with one of those, which, you know, it's not exactly the most efficient way to do things. So you want to bring it barely enough. So don't bring it to over 3. You just want to match the 3. So 2, we'll bring it up to 3. More problems, of course. So we're going to do another type of simplification situation. So let's do 7th root. Let's put some junky numbers. So let us do 25 to the power of 8. A to the power of negative 35. No, that's too nice. 34. All over. B to the power of negative 3 times C to the power of positive 81. So terrible numbers all around. Again, assume that none of these numbers are positive. None of these numbers are 0. This is an odd exponent, fractional exponent, so we're okay with negatives. All right. So where do we even start? Just take a quick survey. We have 7th root, so we have thing number 1 to consider. How many 7s fit in there? Thing number 2, which is a negative exponent, I would pass it to the other side. Thing number 3, again, negative exponent, I would pass it up to the top of the fraction bar. And then this one is right there. How many 7s can fit into there? Well, again, we can start pulling things out of the radical, but let's adopt a different strategy. So instead of starting to simplify at this point, why not just keep things the way they are? And instead, start trying to rationalize some parts. But let's change these to positives first. So equivalent form. 25 to the power of 8, that's left alone. This one passes using the trick. One of your exponential rules, you could just send negative exponents across the fraction bars, thereby flipping their signs. So that's gone. The negative's gone. Send this one down here. Again, the rules are covered in previous lesson. There we go. So we ask ourselves, is this perfectly divisible by 7? No, it is not. What is perfectly divisible by 7? We're already exceeding 7, so we need to bring it up by just one more, and that'll bring it up to 35. This will become 34 plus 1 is 35, which will be divisible by 7. So there it is, but make sure you multiply the top. Extend the fraction bar as a shortcut. Is 81 divisible by 7? No, it is not. It's 1, and so we need to add 3 more, so b to the power of 3. Because, again, 3 plus 81 gives us 84, and then 84 is perfectly divisible by the 7. But multiply to the top as well. And that's the strategy that I would usually use for these type of problems. This is like the maximum amount of work that I would show. And now you just need to start consolidating some of these numbers and then yanking stuff out. Alright, so 7th root. So 25 to the power of 8. Again, we're going to do that momentarily. Make sure you consolidate those ones. 3 plus 3 is 6. But put the a first for alphabetical order. Again, same base, add the exponents, b to the power of 6. And you notice that the 6 is not divisible perfectly by 7, so that's okay. The bottom portions will be divisible, because mechanically that's how we forced it to become. So this one is 35. This one is 84. And then now comes the tedium. How many 7s fit in 8? Just 1. How many 25s did we remove by taking the 7th root? 7, so there should be a leftover of 1 inside the parenthetical. I'm sorry, inside the radical. 25 to the power of 1. Again, how did we yank this out to become this one? Well, because 1 times 7 to put it back in, we'll put back in 25 to the power of 7, and then 7 plus 7 takes you back to this 1. Just to verify the mechanics. Again, this one should not be divisible by 7. This one should not be divisible by 7, so just leave those alone. That's why we chose the nearest number divisible by 7. Don't exceed more than what you need to do. How many 7s fit in this 35? A perfect 5, because again, that's why we chose these numbers. How many 7s fit in there? The perfect 22. Alright, and then since both of these had been successfully removed, this is technically a 1. 7th root of 1 is just 1. So let's beautify the answer. So we have 25 on top. And then times the, again, this one is just 1, so we could just obliterate the bottom. Don't need to write it. 7th root. Copy paste. All over, copy paste. And quick evaluation, none of these values are 0. Negatives are okay. Whole number exponents on the bottom, so we have successfully rationalized no numbers greater than 7 as exponents inside here. So this radical is good. That's just a 25. Nothing special. We can call it right here. Good to go. And again, at this point, I would ask a person. Does that make sense? But I'm just talking to the void. Now let's do some operations now with different exponents, different fractional exponents, which is kind of probably going to be the most complicated situations you would deal with in terms of Algebra 2 / pre-calc exponential situations. So let's see. Let's suppose we have cubic root of 125. We have a to the power of 2, and this is all over b to the power of 5. Already start to survey the problem. You can see you have 3 things. Are they divisible? Are their exponents divisible by 3 times square root? You know what? Let's do 6th root, actually. Let's make things a little easier this time. So 6th root of 625 times a to the power of 5. As you see, this barely misses the mark, so you can't simplify. If this had been 6, please simplify. But it's not. We have b to the power of 4. Very awkward 4. So at this point, we do have an even radicand, so you do need to be mindful of positive, negative nonsense. Let's put in b are positive numbers. Since they're positive, they cannot be 0, because it's going back, flashback to your early days in your mathematical career, you learned that 0 is neither positive nor negative. 0 is the basis for which we define positive, negative. So to the left is going to, the conventional axis is negative, and then to the right, by conventional axis, it's positive. So these are going to be even numbers. Wait, what am I saying? This is just, I'm sorry. What am I saying? 0 is the definition, is how we define positive and negative. I'm sorry. Even odd is basically counting from 0, and then you skip. The next number adjacent is odd, and then the next number is even. Yeah, so if n is the base number, then n plus any sort of increment of whole number 2 is going to get you your next even value. Yeah. That's the definition. Okay. So what I'm saying is this leads to complications, which is why I have to write this part right there. Okay. So evaluating this mess, right? Well, if you realize it, you can see that 125 is 5 times 5 times 5, which is cubic. And then you could just take the cubic right away if you wish. But I'm not going to do it at the moment. I will, however, start to change this one to match this one. So avoiding the translation into fractional exponents, we can keep it as the radical notation. But to get this one to match this one, I'm going to multiply by 2. Okay? So again, this is technically a risky move. So you'll need to double check your answers afterwards. So times 2, times 2, times 2, times 2. But this one I'll change it. No, I'm not going to change it just yet. No, you know what? Never mind. I will change it. It'll be 5. That's the 125. But since we multiply this by 2, this one also exponented by 2. This one changes to a to the power of 4, and then b to the power of 10. Alright, so that's what we did in terms of manipulating the first radical factor, and then this one, of course, is already at 6, which matches this one. So you can just extend this house thing and multiply the entire innards to those things, which is what I'm going to do. So times 625, a power 5, and then the b4 on the bottom. So again, if you're not comfortable doing that at the moment, that's okay. You could just simply copy paste this entire thing here. Might as well break that up. What's that? 625 is 125 times 5, I believe. This is 500. There's 100, so that's 600, and then there's one left over 20. Yeah, 625. Yeah. And then we know that 125 is already this. There are 3 5s multiplied together. Times 1 more 5 is 4. So 4 5s multiplied together, which unfortunately is not divisible by 6. And this one, leave it alone. Leave that alone. Okay, and then once you realize that the radicals are the same types, you can simply multiply inside here with inside there. We've already shown mechanistically why we can do this, so if you need to, back check. Check the VOD. So let's get to combining. This one times this one gives us an obnoxious 14 exponent. Well, PEMDAS first, right? So 3 times 2 is 6, and then 6 plus 4 is 10. A fourth, a 5, so a to the power of 9. Already this looks pretty nice, but we need to rationalize the denominator. So again, at this stage, don't ask yourself how many 6s fit into the 14, because you're going to have to do a little bit of extra work. So instead, rather, how can you bring this up into the smallest number that is divisible by 6? So what is divisible by 6? If you're good at your times table, not 12, it's going to be 18. So we need to bring this up to 18. So you need to add 4. So multiply by b to the power of 4, because again, those two will summate to be 18. But keeping equivalence, the top portion also needs to be multiplied by 4 for one equivalence. Alright. Setup is done, so now just with the follow through. to the power of 10. And then, you know, make sure everything is alphabetical order. For convention's sake, it's power 9. Power 9. Then we have power 4. And power 4 plus 14 is 18. Because we wanted it to be that way. So now we can start yanking things out of the radical. So how many 6's fit into there? Only 1. But if we remove 5, if we remove 6 5's multiplied together, we will still have 4 5's multiplied together inside the radical. So again, the mechanic is 1 times 6 gives you 6, and then 6 plus the 4 takes us back to here. Can we yank out A's? Yes, we can. How many 6 fits into 9? 1. 9 minus 6 is a leftover of 3. Nothing to do with this B, because that's power 4, this is power 6. No whole 6's fit into 4. So you leave that alone. How many 6's fit into the 18? Just 3. So there are no B's left over. So technically B power 0. Right? Again, just to review. How many 6's fit into the 18? 3. So it becomes B to the power of 3 on the outside. How many B's multiplied together did we remove? We removed 3 times 6, which is 18. So technically we have 0 B's multiplied, which is B exponent 1. And if you recall, that's just 1. So there we are. We're going to start moving things. Let's shrink that. Oh, it's too small. Whoops. Okay. At this point, the work's done. Just make sure you write it nicely. Sixth root. Should we multiply this out? I'm not going to do it. A cubed B power 4 all over B cubed. And make sure everything's good, just for habits. B cubed, perfect. It's going to be non-fractional exponent, also not negative. So the bottom looks good. What about here? We have a 4, which is less than 6. 3, which is less than 6. 4, which is also less than 6. This is fully simplified. And then the 5a, nothing to simplify with the bottom. So, should be good. Good to go. Alright, so at this point, I don't think there's... Wait, let's do one more problem, just for good measure, and then that'll be it. So suppose we have fifth root of, let's do something terrible. You know what, not too terrible. That's fine. 16, we'll keep it simple. No, you know what? Let's do 54. And then we have a to the power of 3, so that's like a little bit shy of the 5. And then we have c to the power of 4, which is just 1 shy from the 5. Wonderful. Times. Let's do 7th root. Now let's do square root. Not, I can't make up my mind. Let's do this. Alright, and then we have 36. No, that's too nice. 6 times 3 is 18. Yeah, let's do 18. Let's be obnoxious. 18, and then we have times a to the power 5, c to the power of 21, and then this one more obnoxious thing, negative 2. Alright, so at this point we do have an odd exponent, even exponent. Do we have to worry about negatives? Yes, we do, because remember, this is technically invisible. So that means if c is a negative value and then you raise it to the power of 21, it's still negative. So if that's still negative and neither of these numbers are negative, then you're trying to take the square root of a negative number. And then this one will drift into imaginary numbers territory, which is not what we're covering. So we have to say c is positive. Do we need that for the other ones? Yes, unfortunately, a also has to be a positive number. So again, I'm just being a little pedantic. If this doesn't make any sense, that's fine. It's not the purpose. So this one is also an odd powered exponent. This is technically even. So if b is negative, that would mess things up. Okay. So disclaimer is there. Let me just shrink it. Again, being a little pedantic. Here's the problem. So your job is to multiply and simplify. Seems simple enough. So a quick survey. We have that one. We have we have radical 5 in the radicand, and then we have technically again invisible number 2. So these ones are mismatched. So don't multiply the inside straight up. You have to match the denominators of the fractional exponents. So I'm going to do the easy operation. I'm going to multiply all the exponents by 2 to match this. And all these exponents I will multiply by 5. Again, technically that's not always a safe move for reasons like this. But since I explicitly spelled it out, it is a safe move to do. Alright, so again, we're trying to match up these fractional exponents. So the LCD would be 10. So you got to raise this one invisible 1. So 5 times 2, 1 times 2. 3 times 2, 4 times 2. So there's that. Again, if you had done that, that would have wiped out all the negative signs and would lead us to falsely conclude that this would be legal if there was no disclaimer. This is a 2. We need to bring it up to match the 10, so times the 5. So this is 18 exponent 1, so times 5. Times 5. Exponent times 5. We're not adding 5, so make sure you don't mess that up. We're getting the 2 to become 10 by multiplying by 5, not adding 8, because if you add 8, that's a different operation altogether. That's not distributive property of exponents. Just to reiterate. So this one is negative, what is it? Negative 3 times 5 is negative 15. All over. Oh, that's bad. Again, if you're doing this work, you may feel tempted to bring this out. You can, but I don't prefer to do that. So instead, I'm going to have to deal with this nonsense. This 21 times 5 is 105. Alright, we have successfully matched the denominators of the exponents. So now it's safe to multiply this junk times that junk. And then this one times this one. So 10th root of all those numbers. Unfortunately, this one is quite different from that one. So I'm going to start breaking those ones apart as well. So 54 is 6 times 9, but I'm going to split it into solely 2's and 3's factors. So 2 times 3 will give us a 6. 2 times 9 will give us 18. So this needs to be 4. Wait, no. I'm going to have to factorize 54. So 54 is 6 times 9, which is 2 times 3 squared. Okay, there it is. So this is going to be exponent 3. Exponent 2. So again, I'm just breaking it apart because you're going to have to maybe simplify that depending on teacher. So this one is, ooh, it's a 2. Yeah, it's a 2. So 2 times 9, which is 3 squared. Yeah. So 2 times 3 squared to the power of what? To the power of 5. Delete the intermediate work. Let me shrink this. Or move and then shrink. Yeah. So what have we done so far? We just factorized the 54 into that one, and then we multiplied it to this known value, which we factorized into that one. So we need to take care of the other stuff. So 8 to the power of 6. Let me cross it out so that we don't mix things up. So 8 to the power of 6 times 8 to the power of 25. 8 to the power of 31. So I do suggest you cross things out. Alright, and then the b is awkwardly, there's nothing to multiply by, but it is a negative exponent. So we're going to pass it across the fraction bar. There it is. So this is done. We have a c in the bottom and then c in the bottom, just multiply them straight across. So 105 plus 8, putting it in alphabetical order, is 113. Again, I'm just going to move this perks of the digital medium. We can beautify on the fly. Alright, so we have this. So what do we do now? We ask ourselves, is this divisible by this one? Because we might as well just get to rationalizing right away. So 15 is not perfectly divisible by 10, so we need to bring it up to the lowest and nearest divisible the number that's divisible by 10, which is 20. So times b power 5, but we need to have fractional equivalents, so also exponent 5. This one, is it perfectly divisible by 10? It is not. We need to bring it up to 120, so we need c to the power of 7. Because again, 7 plus 113 is 120, which is divisible by that. Top and bottom. So the entire setup is done. Now we just have tedious cleanup. Unfortunately, I'm going to end up combining this 2 with this 2, so we need to distribute those exponents. Fun times. Alright, so we're going to have 2 to the power of 2, 3 to the power of 6. Make sure you multiply and don't add them, because again, a lot of people, well, I shouldn't say a lot again, but some people mix up the rules and do 3 times 2, but instead they do 2 plus 3. That's times for the distributive property of exponents. And the sad irony is that people screw up the most basic operations in calculus. So they get the calculus right, but they do the basic math wrong. So 5 times 1 is 5. Times that one is 10. Alright. I'm going to copy paste everything. And this is the one where we need to clean up. So b to the power of 20, c to the power of 120. Alright. There are still things to combine. Personally, when I'm doing this work, I would have distribute, and I would have combined them together right there. So mental math, I would have done 2 plus 5 is 7, so I would have written this one directly as 2 to the power of 7. So you can do that if you're comfortable with it. Otherwise, show your work. So 2 to the power of 7, and then 3 to the power of 16. Just to reiterate, feel free to skip your steps if you are comfortable. If you're watching the VOD, let's face it, only people who are watching the VOD can hear these words. And then we have v to the power of 20. So there we go. Now comes the arduous task. Not arduous, tedious. How many 10s fit in there, etc. Nothing to do with the 2s, so you leave the 2s alone. Yeah, so 2 to the power of 7 is left alone. We have some 3s to yank out. How many 10s fit into the 16? 1. So 1 3 gets pulled out. How many do we have left over? 16 minus the 10 that we removed is 6 left over. How many 10s fit into 31? That would be 3. So we removed 30 A's multiplied together, so we have 1 A left over multiplied inside. So make sure you understand this. 3 times 10 is 30. 30 plus the 1 is 31. So we have b power 5, nothing to do with that. C power 7, nothing to do with that. Again, that was a deliberate choice. Bottom portions are very nice though. Of course, we made it that way. So 20 divided by 10 is 2, so b power 2. 120 divided by 10 is 12. What remains on bottom? Well, technically b0 times c0, but don't write that. Write 1 instead. So at this point, we are done, but final cleanup, just to appease whomever is grading you. So there's that. The goofily exaggerated radical signing. Should we multiply that out? No, please no. Perfect. Those ones on the bottom. Alright, and there we have it. Should be the final answer. It's a little cut off. Let me move things over. Oh, whatever. Okay, so final conclusion, and then we are good. At this point, I think that's enough for that. You can end it here, but as a good habit, I'm going to make sure that these numbers are good, however. So will we have broken anything with this final answer? No, because they are all positive numbers. So no zeros on the bottom. No negative numbers here that would break the situation. So we don't need to put absolute value on anything. You know what? Maybe I need to go over that. Yeah, but that's the mechanically heavy type of problem. Let's go back to simpler problems and finally confront the elephant in the room, right? What happens when no specificity is given at the beginning of your problem? So suppose you have cubic root, let's do something very simple. Square root, actually. Let's go back to square roots. So if you're given the square root of 1 over x to the power of 5, for example, and that's all you're given. No disclaimers, nothing. So we're going to proceed as normals. We make note that if you break up the radical, you don't have to do this step. But if you do, you're going to see that the denominator is irrational, so we need to bring it up. So if we leave it as is, we're going to have a fractional exponent, so we're going to have to rationalize the denominator. Remember, invisible 2. 5 is not divisible perfectly by 2, so we need to bring it up. So I'm going to extend this fraction bar times x power 1. Reason being, 5 plus 1 is 6, and 6 is divisible by the 2. What do we get? So we're going to get the square root of x over x to the power of 6. Now we can begin to yank that out. What do we get? X to the power, there's an invisible 2, so 6 divided by the 2 gives us the 3, right? And then we have left over x inside a radical. I'm good to go, right? No! Remember I told you, this is in the denominator. You keep it in the denominator. This is in the numerator, so don't do that. That's somewhat of a mistake. I wouldn't say common pitfall, but it is a pitfall. So again, when you're doing this one, this is in the denominator, so make sure you report it in the denominator once you yank it out. So 6 divided by 2 is 3 beneath the denominator. So put the magic placeholder 1 on top, and then we have a leftover of root x on the top. You know what, let me full notation that. So again, you did 6 divided by 3, so there's a remainder of 0 x's multiplied together right there. So that's technically what you have, but that looks ugly, so let's put it here. This is just a 1, and then the square root of 1 is just 1. So no need to worry about that. So all over x to the power of 3. And typically, you'd be happy if there was a disclaimer up here. But let us check a few things. Well, the original problem was 1 over x power 5. So just by looking at this one, there's something called a domain issue, if you've already stumbled across the concept. They're basically numbers that will break your function, that will cause it to fail. Very similar to like a vending machine. You can think about your function like a vending machine. There are things that you can put into your vending machine and you will get out certain numbers. So if you are in North America and then you have dollars, you would put your coins into the machine. But the machine doesn't take all numbers. So if you try to put in 5 cents, for example, I think most vending machines will not take 5 cents. It will just simply give it back to you. So even if you have enough money with nickels, you're not going to be able to buy what you want. Your function will not be able to take it in. And even worse, if you try to be cheeky and you get a piece of gum, you're like, you know what, I want to get a bag of chips. So you take the gum out from your pocket, and then you try to jam it into the coin slot, it ain't going to work. It will cause your function to break, and then someone's going to have to repair it. Same thing here. This is a function. It only takes in certain values. If you try to take the square root of a negative, it will break your function. So we make note. Number 1, what's happening to this x? X is being raised to the power of 5. So if it was a negative number, it will remain a negative number. 1 over a negative number will still get you a negative number. This one, red flag, if you haven't covered imaginary numbers, you would have to put not possible, undefined, or empty set, no real solution. Yeah, there you go. Empty set, no real solutions. So this is pretty much the same as this. If you get a negative inside even-powered radicals. Alright? So, this one, we're just evaluating the situation. This was our answer, but you need to specify when your answer is valid, and it's only valid when this thing is valid. So number one, there are two things. X cannot be negative. And then number two, you have another separate issue. This is a fraction, and if you recall earlier days, you cannot divide by 0. Dividing by 0 is undefined. So there are two numbers. Number one, x cannot be negative because it will break your radical function. And then number two, x cannot be 0 because that would break your inner function, which is the fractional situation. So two situations will break your function. Technically, this is an infinite situation, right? Because all the negative values will not work. So when you report your answer right here, you have to report two things. You have to qualify your answer in two ways. So number one, x is not a negative value. I don't think anyone writes this notation. And then number two, x is not 0. But this is very wordy. So let us be concise. Let us aim for concision, right? So x is going to be greater than 0, and that takes care of both of these conditions. Both of those conditions you can consolidate nicely with this statement. All right. So those are the type of nuances that you have to watch out for. But of course, there are nuances within nuances. What if you took the square root of 1 over a to the power of 4? At this stage, you might be tempted, like, okay, this is we're trying to take the square root. If a is a negative value, that should be okay, right? Because if you raise well, maybe they changed this to 6, actually. For reasons. So if you try to take the square root of negative value, so if a is negative, this is just running through the scenario, if a is negative and you raise it to the 6th power, then it should become positive, right? Once you have a positive number, it's not 0, so it's okay to be within the fraction. So this one will overall be square root of a positive number, and this one is a workable situation. So it looks good, right? But hold on. Let's check it out. So running through the numbers, again, if it's divisible 2, how many 6s? This is a perfectly divisible by 2. Make sure this is under this is in the denominator, so make sure you report it back. So what is the square root of exponent 6? It's just 3. And of course, the square root of 1 is just 1. So, is this answer good? And in short, no, it is not good. Unfortunately, you have to... Wait, are we good? Well, let's consider. If a was a negative number, was it a safe situation? Will we get exactly what we expect? No. Okay, here's the reason why. So, just checking this one, if a had been negative, it would have been safe, right? So you would get an overall positive value. But a is negative, but if you write your answer like this, you are saying that the answer is a negative value. But that can't be, because the square root of a value would never report negative in the aftermath. So here's what I mean. So if you have the square root of a negative 9, you can't do this unless you have the imaginary number concept. You can't just say, oh, well, I could do the square root of this. It's just going to be 3, and then you just copy paste the 3 out. You cannot do that. Because if you check it, that's going in the direction of the inverse. So if you go quote-unquote forwards, what is negative 3 times negative 3? It is most certainly not negative 9. So that's why it fails, and this is why we have to do this consideration in the first place. So again, reaching this particular answer, this answer is incorrect. You would be deducted points if you were getting graded for this. So technically, you have to put absolute value. You are basically obliterating the negative value from your answer. But it's easier to see it with just the basic square root. So again, if you take the square root, if I explicitly told you the answer, I'm telling you right now, the answer to this question is 9. I'm telling you directly right now. Actually, no. The answer is positive 3. Okay? So if I give you this particular problem, and I'm telling you this is the answer, I want you to solve for x. So how do you solve for x? Two methods. You can try to square both sides first, or you can apply this radical directly to this 2. And we're going to use the latter method. Again, fractional exponent, this is technically 1/2. 1/2 distributive property of exponents to this 2 will get you positive 1. Does positive 1 equal to 3? Yes, it does. It actually matches the answer, because I told you this is the answer. Right? But here's where complications arise. Suppose in my mind's eye, the answer that I wanted was negative 3. Okay? Because negative 3, if you square negative 3, it's positive 9. And then the square root of 9 is actually 3. Yes, that is correct. So let's do this problem without any considerations at all. So again, you're applying the square root to this one. You get exponent 1. X is equal to 3. You think that's the answer. Unfortunately, that's not what I had in mind. So you would be wrong. So when you apply the exponent of 2 to this one, you are transitioning from even exponent into odd exponent. So you must account for possible scenarios. So you have to put plus or minus 3. Or, in other words, absolute value of 3. What am I saying? 3. Absolute value of x is equal to 3. And from here on, you can generate the two scenarios. So 3 could be a positive number, or x could be a negative number. I keep saying 3. So x could be a positive version of 3, or x could be a negative version of 3. And those are the two answers you would report. You would say this one or that one. And that's true, because that's what I had in mind. So what does that all mean? Basically, anytime you transition from even powered exponent let's do 4. So fourth root, if you transition from even powered exponent to odd powered exponent, there is a shenanigans with the plus or minus, so you have to account for that. So this is 10th root of a to the power of 50. So when how many 10s fit into 50? Only 5. Do not write this as your answer if you have no what are those called? Disclaimers. So you have to put, whoops. So you'd have to put absolute value. Alright? If, however, you have something like 10th root, this is the one I was originally going to go for, to the 40th, so how many 10s fit into 40? It would be 4. Should you be safe and put absolute value? No, you don't have to put absolute value. Because the exponent 40 is even, it's still even. Which means, if a had been a negative value, it would have been changed to positive. if a is negative, it would still be positive right here. So you don't need to put absolute value for this situation. And just for completionist's sake, what if you had odd on the outside, then you had even on the inside, right? So if a is exponents 9, for example. So in this situation, how many 3's fit into 9? Only 3. So do we need to put absolute value for this one? No, you don't. Reason being, this is cubic root. Cubic roots are a function where you can take negative values. Case in point, if you had negative 9, for example, no, I'm sorry, negative 27, for example, if you think about it, can we evaluate that negative sign? Yes, we can. If you think about it, negative 27 could be negative 3 times negative 3 times negative 3. Because in this case, the negative signs will not negate each other. So consolidating all that, negative 3 to the power of 3, this one divisible by this one, you get negative 3 back. It's okay to have a negative answer when it's odd. So yes, you don't need to put this. In fact, if you put this, I think you may be deducted, depending on how strict your teacher is. No, it's definitely wrong. If you put absolute value, it's definitely wrong. If a is negative, you force the negative out. So putting absolute value, you should be deducted points. And I think to cover the last of these 4 scenarios, what if you have odd, and then you had even right here? So how many 3's fit into the 6? 2 of them, so a to the power of 2. Do we need to put absolute value right here? And no. Because if a had been negative, the negative sign will be obliterated by the 6. So your answer straight up would be positive. If a is negative in the beginning and you squared it, it will be positive. So that's okay. It will be consistent overall. So no need to put absolute value for this one. So the only scenario really is going to be this one. And I think that's about covers it. I think for the next stream, I'm just going to cover a bunch of problems. So here we're working on, for this particular stream, we worked on kind of the mechanics about why you can use shortcuts. So once those shortcuts have been shown for marathon problems, you don't need to show those work over and over and over again, because that's going to really stretch out the time. So again, I'm thinking for the next stream, I'm just going to be doing a bunch of exponential problems using the tools that we've learned. In other words, no logarithms, no taking, you know what, maybe we can exponentiate both sides, so we'll see. But that's it for this particular stream. I may be streaming later, but I guess that's needless to say since there's nobody in the chat. So that's it for this one. I'll see you next time, which may be the next stream. So until then, you have yourself a good one.